Welcome! In this session, we're tackling LeetCode problem number 1961, check if string is a prefix of array. This is a straightforward string manipulation problem where we'll determine if a given string is a prefix of an array of strings. Let's dive in and break it down step by step. In this problem, we are tasked with determining if a given string, denoted as S, is a prefix string of an array of strings called words. A string S qualifies as a prefix string of words if it can be formed by concatenating the first k strings from the array, where k is a positive integer and does not exceed the length of the array. Essentially, we check if combining the initial elements of words in order can construct the string S. The input consists of the string S, which is made up of lowercase English letters, and words, which is an array of strings also containing only lowercase English letters. The output is a Boolean value, true if S is a prefix string of words, and false otherwise. Let's look at an example to clarify the problem. Suppose S is a love LeetCode and the array words is, I, love, LeetCode, apples. To check if S is a prefix string, we take the first few elements of words and concatenate them. Starting with I, then adding love, and finally LeetCode, we get a love LeetCode, which matches the string S. Since S can be constructed by concatenating the first three elements of words, we return true. This demonstrates how the prefix condition is satisfied when S matches a concatenated sequence from the start of words. Now, consider another example where S is a love LeetCoding and words is the same array, I, love, LeetCode, apples. Here, no prefix of words can combine to form S. If we concatenate I, love, and LeetCode, the result is a love LeetCode, which does not match a love LeetCoding. Even if we include apples, the result becomes a love LeetCode apples, which still does not equal S. Since none of the prefixes of words matches S, the output in this case is false. In another example, let S be hello and words be, hello, world. Here, the first string in words is hello, which directly matches S. Since S can be formed by taking just the first string from words, the prefix condition is satisfied, and we return true. This case highlights that even a single string from words can qualify as a valid prefix, as long as it matches S. Now, let's consider some edge cases. If S is shorter than the concatenated prefix of words, such as S being ABC and words being ABCD, then S cannot match any prefix, and the result is false. On the other hand, if S exactly matches the concatenation of elements in words, for example, S equals ABC and words is the result is true. Similarly, if S is longer than all possible concatenations of words, like S being ABCDF and words being ABC, the result is false. Finally, if words has many strings but only a small prefix matches S, such as S being ABC and words being BECD, then the result is true because the concatenation of the first three elements matches S. These edge cases help clarify how the solution behaves under different scenarios. To solve the problem of determining whether a string S is a prefix of an array of strings words, we need to check if S can be formed by concatenating the first k strings in words, where k is a non-negative integer less than or equal to the length of the array. The brute force approach offers a simple way to tackle this problem. The idea is to incrementally concatenate strings from the array and compare the result with S at each step. If the concatenated string matches S, we return true. If it becomes longer than S or all strings are processed without a match, we return false. This approach involves initializing an empty string called prefix, iterating through each string in the array, appending it to prefix, and checking after each append whether prefix matches S or exceeds its length. While straightforward, this approach has a time complexity of n*m, where n is the number of strings in the array and m is their average length, making it less efficient for larger inputs. The brute force approach, while intuitive, has inefficiencies because it repeatedly builds the prefix string. A more optimized approach eliminates this overhead by leveraging slicing and direct comparisons. Instead of concatenating strings, we use two pointers, one to traverse S and another to iterate through words. As we process each string in the array, we check if S starts with the strings processed so far. If at any point S does not start with the expected string, we return false. If the pointers align at the end of S, we return true. This strategy involves tracking progress through S using a pointer. For each word in words, we check if S contains the word exactly at its current position using slicing. If it does, we advance the pointer by the word's length, if not, we return false. Finally, we ensure the pointer has reached the end of S. This optimized approach has a time complexity of O, n plus m, where n is the length of S and m is the total length of all strings and words, and it uses constant space. The key insight that makes the optimized approach more efficient is realizing that we don't need to explicitly build the concatenated string. By directly comparing substrings of S with elements of words, we avoid the computational overhead of string concatenation and reduce unnecessary operations. This approach is preferred because it is both time efficient and memory efficient, with linear time complexity relative to the size of the inputs. Additionally, it simplifies debugging since it uses straightforward comparisons rather than managing intermediate strings. However, there are trade-offs to consider. The brute force method is more beginner-friendly and easier to implement initially, but it becomes impractical for larger inputs due to its quadratic time complexity. On the other hand, the optimized method, while slightly more complex, is far better suited for handling larger datasets. The final algorithm is straightforward to implement and strikes a balance between simplicity and efficiency. Here is the Python implementation of the optimized solution. The function iterates through words while maintaining a pointer to track progress through S for each word. It checks whether the current substring of S matches the word exactly by using slicing. If S starts with the word, the pointer is advanced by the word's length. If not, the function immediately returns false. If the pointer reaches the end of S, the function returns true, confirming that S is a prefix of words. This implementation avoids unnecessary concatenations and is designed to terminate early if a mismatch occurs, making it both efficient and effective for solving the problem. The problem asks us to determine whether a given string S is a prefix of a concatenated sequence formed from the initial portion of an array of strings called words. To do this, we incrementally build a concatenated string from the array and compare it to S. The goal is to find if S matches the concatenation of the first k strings and words, where k can range from 0 to the length of the array. We start by initializing an empty string, concatenated, which will hold the progressively built sequence. This allows us to compare intermediate results with S, providing an opportunity to stop the process early if a mismatch is detected. Then, we iterate through each string in the array, appending it to concatenated while checking if S starts with the current concatenated value at every step. The core operation here is the prefix check, which is efficiently handled by Python starts with function. By calling s.starts with concatenated, we can confirm whether the current concatenated string matches the beginning of S. If at some point the concatenated string becomes exactly equal to S, we return true, as this means S is a prefix of the array. However, if the concatenated string grows longer than S, we immediately terminate the loop and return false, as it's no longer possible for S to be a prefix. This early termination significantly optimizes the process by avoiding unnecessary computations. Finally, if the loop completes without finding a match, we return false, indicating that S is not a prefix of the array. One key insight in this approach is the use of early exits to improve efficiency. By checking the length of the concatenated string against S, we prevent redundant operations, especially in cases where the prefix check fails early. Additionally, leveraging starts with ensures that mismatches are detected promptly, which is particularly useful for longer strings or arrays. There are also important edge cases to consider. For example, if S is empty, it will always be a prefix, so we return true. If the array words is empty, S can only be a prefix if it is also empty. Finally, if the concatenated string exceeds the length of S at any point, we immediately return false, as this guarantees that S cannot be a prefix. This algorithm relies on simple yet efficient data structures. The variable concatenated is used to incrementally build the concatenated sequence, ensuring low memory usage while allowing efficient prefix checks. The array words is traversed sequentially, aligning naturally with the logic of prefix determination. For complexity analysis, the time complexity is O, n, where n represents the total length of all strings and words. Each string is processed once, and the prefix check using starts with runs in linear time relative to the length of concatenated. The space complexity is O(1) in terms of additional memory, as we only use the concatenated variable, making this approach both time and space efficient. Let's walk through two examples to illustrate the algorithm in action. In the first example, S is a love, and the array words is I love LeetCode. We start with concatenated as an empty string. Appending I gives concatenated equals I, and s dot starts with I returns true. Next, appending love results in concatenated equals love, and s dot starts with love is also true. Since concatenated now equals s, we return true. In the second example, s is a love code, and the array is the same. After appending I and love, we have concatenated equals love, which still matches the prefix of s. However, appending LeetCode gives concatenated equals love LeetCode, which no longer matches s. Thus, we return false. These examples demonstrate how the algorithm effectively handles both matching and non-matching cases. This Python solution solves LeetCode problem 1961, check if string is a prefix of array. The task is to determine if a given string s is a prefix string of an array words. Explanation of the code. 1. Initialization. The variable concatenated is initialized as an empty string. This will be used to build the prefix string incrementally by concatenating elements from the words array. 2. Iterating through the words. The function loops through each word in the words list. For each iteration, the current word is added to the concatenated string. 3. Prefix check. After each concatenation, if the concatenated string matches s, the function immediately returns true since s is confirmed as a prefix. If the length of the concatenated string exceeds the length of s, the function returns false early, as it is impossible for s to be a prefix. For default return, if the loop completes without finding a match, the function returns false, indicating that s is not a prefix of the words array. Edge cases handled. Empty words array, the function will return false since no prefix can be formed. When s is an empty string, the function will return true, as an empty string is a prefix of any array. When s is longer than the concatenation of all words and words, the function will return false. Complexity. Time complexity. The function performs a single pass through the words array and concatenates strings. The complexity is O(n), where n is the sum of the lengths of all strings and words. Space complexity. The space usage is O(1), excluding the input, as the solution uses a single string variable for concatenation. This approach is efficient and directly matches the problem requirements. It ensures correctness by checking the prefix condition at each step and avoids unnecessary computations by returning early when possible. This is the Java implementation of the LeetCode problem, check if string is a prefix of array. The logic mirrors the Python solution, using a string builder to efficiently concatenate strings while iterating through the array. The method checks if the concatenated string matches the target string s or becomes longer than s, ensuring an early exit when possible. Differences from Python include explicit type declarations and the use of the string builder class for mutable string operations. To solve this problem, we start by initializing some variables. The string s is given as a love LeetCode, and the array words contains I, love, LeetCode, apples. We also initialize an empty string called concatenated to build a cumulative string as we iterate through the words array. In the first iteration, the current word is I. We append this word to concatenated, so it becomes I. At this stage, we check if concatenated is equal to s. Since I is not equal to a love LeetCode, we proceed to the next condition and check if the length of concatenated exceeds the length of s. Here, the length of I is 1, which is less than 12, so we continue to the next iteration. In the second iteration, the current word is love. Adding this to concatenated updates it to a love. Again, we check if concatenated equals s. Since love is not equal to a love LeetCode, and the length of a love is still less than 12, we proceed further. In the third iteration, the current word is LeetCode. Adding this word to concatenated results in love LeetCode. This time, when we compare concatenated with s, they are equal. Since we've found a match, we return true. This means that the string s is indeed a prefix formed by concatenating some or all elements of the words array in order. For the next example, we initialize s as love coding and words as I, love, LeetCode. Like before, we set concatenated to an empty string to start building the prefix. In the first iteration, the current word is I, and appending this to concatenated results in I. Since I is not equal to s and its length is less than 11, we continue. In the second iteration, the current word is love. Adding love to concatenated updates it to a love. We check again if concatenated equals s, but a love is not equal to a love coding. The length of concatenated is 5, which is still less than the length of s, so we proceed to the third iteration. Here, the current word is LeetCode. Appending this to concatenated results in elove LeetCode. When we compare this with s, it is clear that elove LeetCode does not match elove coding. However, at this point, the length of concatenated becomes 13, which exceeds the length of s. This tells us that it is impossible for s to be a prefix of words, so we return false. This concludes the second example. In the third example, s is initialized to a, and words contains b, c, d. As usual, we start with concatenated as an empty string. In the first iteration, the current word is b. Adding b to concatenated results in b. Comparing concatenated with s, we see that b is not equal to a. Next, we check if the length of concatenated exceeds the length of s. Here, the length of b is 1, which is equal to the length of s. Since no prefix match is possible beyond this point, we immediately return false. This shows that s is not a prefix of the words array in this case. Here, we analyze the time complexity of the solution step by step. First, the algorithm iterates over the words array, processing each word one at a time. If the array contains m words, this operation has a linear dependency on m. Next, for each word, the algorithm concatenates it to the concatenated string. In Python, the plus equals operator creates a new string, so the cost of each concatenation depends on the lengths of the strings being combined. Over the course of the algorithm, the total number of characters concatenated is at most equal to the length of the target string s, denoted as n. This means the cumulative cost of all concatenations is proportional to n, resulting in O(n). Lastly, after each concatenation, the algorithm compares the concatenated string with s. Comparing two strings involves examining their characters up to the length of the shorter string, which in this case is s. In the worst case, each comparison takes O(n). The overall time complexity of the algorithm comes from the combination of concatenation and comparison operations. Both of these processes scale linearly with the length of s, meaning the total time complexity is O(n). Now, moving to space complexity, the algorithm uses an auxiliary string, concatenated, to build the prefix incrementally. In the worst case, this string grows to the full length of s, requiring O(n) additional space. The input words in s themselves are read-only, so they do not contribute to the additional space usage. As a result, the overall space complexity is also O(n), driven solely by the storage required for the concatenated string. Now let's consider the best, average, and worst case scenarios. In the best case, the target string s matches a prefix of words early, perhaps after just a few words. Here, the algorithm exits as soon as the match is found, and the time complexity depends on the length of the matching prefix, denoted by k, where k is less than n. This gives a time complexity of O(k) for the best case. On average, the algorithm processes a portion of the words array, with the time complexity depending on how quickly a match is found. This typically results in an average time complexity of O(n). In the worst case, where s either does not match any prefix or matches the entire concatenation of words, the algorithm processes all characters up to the length of s, leading to O(n) time complexity. Comparing this to a brute force approach, which would involve generating all possible prefixes of words and comparing each to s, the brute force method would require O(n)² time because each comparison involves copying strings. By building the prefix incrementally, the current solution avoids this inefficiency, reducing the time complexity to O(n). Mathematically, the dominant cost comes from string concatenation and comparison, both of which scale linearly with n. Similarly, the space complexity is dominated by the concatenated string, which grows to O(n). When tackling this problem, there are a few common mistakes to watch out for. One of the most frequent errors is not handling partial matches correctly. Instead of stopping at the first mismatch, many solutions unnecessarily continue concatenating the strings in the array, which wastes computation and can lead to incorrect results. To fix this, you should stop concatenating as soon as the combined length of the strings exceeds the length of S or when a mismatch is found. Another common issue is ignoring edge cases. For instance, what happens if S is empty, or if words is empty? Or if S is longer than all the strings and words combined? These scenarios are often overlooked, so it's important to add explicit checks to handle them before iterating through the array. Additionally, some solutions attempt to concatenate the entire array upfront and only then check if S is a prefix. While this approach might seem straightforward, it's inefficient in both time and space. A better approach is to concatenate incrementally and stop as soon as you know the result. Lastly, incorrect indexing is another common pitfall. This happens when solutions improperly slice S or compare it with the wrong subset of strings from the array, leading to off-by-one errors. To avoid this, ensure you carefully track and test all index boundaries in your code. Another mistake to be mindful of is assuming that all strings and words are non-empty. If words contains an empty string, it can disrupt the logic of your prefix checks. To prevent this, include checks for empty strings wherever it's relevant. Now, as you approach an interview setting, here are some insights to keep in mind. First, prioritize writing an efficient solution that avoids unnecessary concatenation. Incremental checks using string slicing and early termination not only make your solution optimal but also demonstrate strong problem-solving skills. This problem is a great example of prefix matching, which is a fundamental string manipulation technique. It tests your ability to work with strings and arrays together, so focus on showcasing this capability. Aim for optimal time complexity, ideally O(n), where n is the length of S. This can be achieved by avoiding redundant operations. And remember, clear communication is key in interviews. Be ready to explain how you handle edge cases, as interviewers often evaluate how well you can anticipate and address these scenarios. This problem also ties into several related problems that you may encounter. For example, LeetCode problem 14, longest common prefix, shares a similar concept where you work with prefixes, but it involves finding the longest common prefix across multiple strings. Another example is LeetCode 28, implement strstr, which focuses on substring matching, a foundational operation in string manipulation. LeetCode 58, length of last word, is another string-based problem that requires careful handling of edge cases, and LeetCode 1816, truncate sentence, involves working with parts of a string, which is conceptually similar to this problem. Beyond these connections, there are alternative approaches to solving the problem, each with its own trade-offs. The most optimal approach involves incremental concatenation with early exit. Here, you gradually concatenate strings from words until the length of S is reached or a mismatch occurs. This approach has O(n) complexity since you only process as much of the input as needed, and it minimizes memory usage. However, it does require careful tracking of concatenation progress to ensure correctness. Another approach to consider is full concatenation followed by a prefix check. This method involves concatenating all strings and words upfront and then checking if S is a prefix of the result. While this approach is easier to implement, it's less efficient, with a complexity of O, k plus n, where k is the total length of strings and words and n is the length of S. It also wastes resources when S is not a prefix early on. A third option is character-by-character comparison. In this approach, you compare each character of S with the corresponding character from the concatenated strings of words. This eliminates the need for explicit concatenation and achieves O(n) complexity. However, it requires careful index management to ensure that you're accurately comparing the right characters at each step. Each of these approaches has its pros and cons, so understanding their trade-offs is crucial for selecting the best solution in a given context. Great work! To summarize, we solved check if string is a prefix of array by iteratively building the prefix string and comparing it with the target. This problem reinforces key string manipulation techniques. Thanks for joining, and don't forget to subscribe for more coding tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!